Hi everyone, Mr. Mitchell here. I'm going to try to annotate these notes as we go along for you. I just tried to do it and I ran out of time. Apparently I have a 15-minute time limit here, so I'm going to try to talk a little bit faster, cut down what I'm going to say so we can get through all this. So today we're going to be looking at motions. So the Earth, it has two different motions. It rotates, it spins on an axis. You can imagine a big rod being stuck through the Earth from North Pole to South Pole and the Earth spinning on it. And that rotation takes 24 hours, one day. We also revolve around the sun. And this is where the Earth follows an orbit around the sun. And our orbit takes 365 and a quarter days. It's not a completely round orbit. It's more of an elongated circle called an elliptical. And sort of a fun fact here, in the summer or in the wintertime in the northern hemisphere, we're in the northern hemisphere, north of the equator, we are actually 5 million kilometers closer. And we'll talk about that a little bit later. Sometimes we are closer to the sun in our orbit, sometimes we're further away or somewhere in between. If you took the average distance that we are away from the sun, that would be our orbital radius. What determines how long it takes for a planet to go around the sun? Two things. One, obviously the planets that are further away have a much longer distance to travel, so that's going to make them it's going to take longer. But also, the further you are away from the sun, the slower you are going through space. So Mercury, 88 days, short path, moving very fast. Neptune takes a long time, longer path, and it's moving slower. Historically, our ancestors would have looked at the solar system from a geocentric model. This is where the Earth is the center of everything. And this actually kind of makes sense. So we have the Earth here, the moon, of course, we can see it moves through the sky, it's revolving around us. Planets appear to move through the night sky, so they appear to move around us, as does the sun. In the morning, the sun comes up in the east. Through the day, it moves through the sky over top of us, and it finally settles in the west. So it appears to move, but of course, this is not the case. The correct model is a heliocentric, helio being Greek for sun. It's the sun-centric model where everything revolves around the sun. And we know that's the case. With the exception of the moon here, it doesn't revolve around the sun. Well, I guess it sort of does, but it revolves around the Earth. Motions of the moon. So the moon exhibits the same motions that the Earth does. It spins on its axis, and it also revolves around the Earth. Now, both take the same amount of time. So the Earth spins or revolves once a day, every 24 hours. It takes about a month for the moon to do the same thing, one rotation in a month. It also will revolve around the Earth every month. And because they're both moving both motions are sort of at the same speed or temporal speed anyways, about every 30 days, we only ever see one side of the moon. So as the moon is rotating, the same side is constantly facing us. Gravitational force, this is a force of attraction between all masses. The greater the mass, the stronger the force. And it's a gravitational force that keeps planets from flying off into space. It keeps them revolving around the sun. The Earth's tilt. The Earth is tilted at 23.5 degrees. And this tilt is really important because it's responsible for our seasons. I already mentioned in our wintertime in the northern hemisphere, we're closer to the sun. So let me talk about that for a moment here. So here's the sun, and here is the Earth in two different positions. Over here is us in the wintertime. So here's the equator, and Whippy here, we're north of the equator. In the wintertime, we are tilted away from the sun in our orbit. And because of that, the sun's energy and its rays are spread out over a greater landmass when they hit the Earth. And because of that, because they're not concentrated, the weather in the northern hemisphere is colder here. In the southern hemisphere down in Australia, it's their summertime. You can see that they're tilted toward the sun at that point. Fast forward 6 months, and we're now into summertime in the northern hemisphere. So Whitby up here is tilted toward the sun. The sun's energy and rays are focused in on Whitby, and it's nice and warm. Conversely, down here in the southern hemisphere in Australia, the Earth is tilted away from the sun, so it's their wintertime. Just backing up to this diagram here, you can see 4 different positions. So the winter solstice in the northern hemisphere tilted away from the sun. It's also the December 22nd is the shortest day of the year. It's still 24 hours, but when we say shortest day, it's the least hours of sunlight. So we have the least hours of sunlight on this day. Conversely, summer solstice in around June 21st, 22nd, we are tilted in the northern hemisphere toward the sun. We have the most hours of sunlight. If you think of mid-June there, we can have it gets bright before 6 in the morning, and it's often close to 10 o'clock at night before it gets dark. And halfway in between, in March and in September, we have the equinoxes. This is where we have 12 hours of daylight, 12 hours of sunlight. And even though the Earth is tilted, in these 2 positions in the orbit, not tilted toward or away from the sun. And as I mentioned, in this right here in the winter, we are actually 5 million kilometers closer, but that being tilted away from the sun, and that sun's energy being spread out over a greater area is what makes the weather cooler. Now, I did mention that there's 365 and a quarter days in a year. And that's important. So it takes 365 days for the Earth to do a rotation, but it's 365 and a quarter days. And what we do is we add those quarter days up, and every 4 years, we add those quarter days together and we get 1 full day, and we add that onto our calendar. 2020 was a day that we added that onto our calendar, and we got February 29th. It's a leap year. The reason we do that is in the northern hemisphere, in this position in the orbit, December 22nd, we expect it to be cold. And over here in the summer, June 22nd, we expect it to be warm. Well, if we didn't add that extra day on, what would happen is the Earth would be in a different spot in its orbit on December 22nd. So December 22nd, we expect the Earth to be in this spot on its orbit, and because of the tilt, we're getting winter weather. Well, over the course of 100 years, could be one of our lifetimes, if we didn't do that, what would happen is the Earth would be in this position on December 22nd. And in another 100 years, it would be in this position. And in about 300 years, it would be in this position. So December 22nd would be in this spot of the orbit, experiencing spring weather rather than winter weather. And likewise, over that same amount of time, whether the Earth being here, experiencing summer weather, it would be here starting to experience fall weather. So we do attribute that just to keep the Earth in the same spot in the orbit on the same day. We add in that leap year. Eclipses. There's 2 different types of eclipses. A lunar eclipse, this is where the moon gets into the Earth's shadow here. A full eclipse only takes a couple minutes. The whole process might be, say, an hour, where, remember, the Earth is in movement, is constantly moving, as is the moon. So when one of these is going to happen, you can see the moon start to move into the shadow, and it might take a half hour to finally get fully engulfed in our shadow, and then it starts to move out of our shadow a couple of minutes later. So then it's a partial eclipse, and finally until it's right out of our shadow. And we have here a solar eclipse. This is where we where the moon gets between us and the sun. You can see a picture of one here. This is the moon, and it's blocking out the sun. This is only visible from certain places on Earth. So if you're in Whitby, Ontario, you might see a full eclipse where the sun is totally blocked. But if you were to drive a few hours away to, say, Montreal, you might only see a partial eclipse, or only part of the sun is blocked out. So it depends on where you are on Earth. So when an eclipse occurs, It's a full eclipse for some people, it's a partial eclipse for other people, and other places on Earth there's no eclipse at all. They still have a full view of the sun. Tides are caused by the difference are caused by the difference between the force of gravity in the side of the Earth nearest the moon and the force of gravity on the other side. So basically, it's the moon's that causes the tide. The moon's gravitational pull does pull the ocean water toward it, and because of that, the side facing of the Earth facing the moon and the opposite side of the Earth get a high tide where water levels are higher, and sort of these lateral areas here, you get a lower tide area. So take a few moments, ladies and gentlemen, read over these notes. Hopefully my explanations have helped out a little bit. Check out the videos I put there as well, and take care of yourselves, and we'll see you soon.